Hello everyone, this is Dr. Indradeep Kumar, Associate Professor, IARE, Hyderabad. So in this video, we will see deflection of open and closed section beam. Okay, so our lecture topic will be what? Deflection of open section beam and deflection of closed section beam. So first let's start with the deflection of open section beam. Okay, bending, shear and torsional deflection of thin wall beam are readily obtained by application of unit load method. So what we are doing, the shear stress and torsional deflection, we are obtaining by applying the unit load method. Means uses unit load applying. The displacement in a given direction due to torsion is given directly by that displacement delta T is from overall the entire length L T naught T1 by G J into dz, where J is the torsion constant. Okay, depends on the type of beam under consideration. So which type of beam we are taking that have the different torsion constant, so that J is a torsion constant. Okay, expression for the bending and shear displacement of unsymmetrical thin wall. Unsymmetrical, just see that word. Unsymmetrical thin wall beams may also be determined by the unit load. So even for symmetrical or unsymmetrical, also we can determine by the unit load method. They are complex for general case and are most easily derived from first principle by considering the complementary energy. So what we can do, we can just see earlier also we had seen in that one complementary energy method, but wherever the complex problem is there, that we can solve by the complementary energy method. So here again that concept only of the elastic body in terms of stresses and strain rather than load and displacement. So now instead of considering load and displacement, because we are applying the load and we are getting the displacement, so we should use that one, load and displacement. But what, by the complementary energy method, there already we had seen we are using stress, strain instead of load and displacement. So again we can use here, now we will use here that stress and strain instead of load and displacement. Okay, we observed that the theorem of principle of a stationary value of the total complementary energy of an elastic system is equivalent to the application of the principle of virtual work, where virtual work acts through real displacement. This already we had seen in the complementary energy. Whatever the virtual is there, that will opposite of that is the complementary energy. We may therefore specify that in our expression for total complementary energy, the displacement or the actual displacement produced by the applied load, while the virtual force system is the unit load. So what we can do, we can say that whatever the displacement is there or whatever displacement produced, that is because of the applied load, and because of whatever the virtual force is there, that is the unit force. Just that we are assuming. Considering deflection due to bending, the increment in total complementary energy, just here, considering deflection due to bending, right, because of the force here. Now we are considering the bending also. So bending, the increment in for total complementary energy, so the amount which the complementary energy will increase due to application of virtual load is, so because of this virtual load, that unit load, right? What will be there? Yeah, L, for L, A sigma Z1, that L into strain, sigma Z into strain into dA. So sigma Z comma 1 into epsilon Z comma 0 dA into dz plus that this T delta M, right? Or for that's strain into delta M, where sigma Z1 is the direct stress at any point in the beam cross section corresponding to the unit load. This stands for the unit load. So because of unit load, okay, is the strain at the point, that sigma, and sigma Z0 is the strain at the point produced by the actual loading system. Okay, so this is that one for because of the that unit load. That's why here also that one is there. Okay, further, delta M is actual displacement due to bending at the point of application. That's why there one is there, and in the direction of the unit load, and unit load, so 1. Since the system is in equilibrium under the action of unit load, the above expression must equal to 0. Hence, right, that just here this equation must be equals to 0, right? Or so after that, just take this whole thing to the other side. So means what we will get, the delta M, okay, is equals to this minus term becomes positive. So L, okay, closed integral of overall, then this sigma z comma 1 into epsilon z comma 0 into dA into whole dz. Right, that one. Yeah. Okay, that integral of this. Okay, now sigma z1 is that already we had seen that one. Sigma z means just one stands for where the unit load is acting. So here don't get confused what is one, what is that one. One is where the unit load is acting. So sigma 1 that already we had seen my ixx in the previous video, that my ixx and mx was there. So here let's see here. So my comma 1 ixx minus mx comma 1 ixy by ixx iyy minus I square xy. So this already we had seen into x plus mx comma 1 into ixy minus my comma 1 into ixy by ixx into iyy minus I square xy. So this is for the y term. So into y. Okay. Now, so just take here that one. So this is for what? The stress. What is the strain? Sigma by E. Why? From the Hooke's law, right? That sigma is directly proportional to, that stress is directly proportional to a strain. So sigma equals to E into a strain. So a strain is what? Sigma by E. So this sigma we have, just divide by E. We will get the strain. So strain equals to 1 by E. Or this we can write as sigma into 1 by E. So 1 by E taken common, and this whole the value of this sigma. So now we got sigma. So just here sigma z comma 0. So that's why just replace wherever 1 is there to 0. So sigma my comma 0 ixx minus mx comma 0 ixy by ixx iyy minus I square xy. So wherever 1 is there, just replace with 0, because here we are finding for sigma and this is for the virtual load where it's acting. Okay, plus mx comma 0 iyy minus my comma 0 ixy by ixx into iyy minus I square xy into y. So now we have what? Stress and strain at that comma 0, where the suffix 1 and 0 refers to the, just see here, unit load and actual loading, right? So 1 is for unit load and 0 is for actual loading in the system, and xy are the coordinates of any point in the cross section referred to the centroidal system of axis. Just xy wherever is there in that according to that axis. Okay, now substitute the value in the previous equation. The substituting for sigma z1 and epsilon z0 in moment equation. So which one is our moment equation? Here, right? Let's substitute these two values into dA whole integration of dz. Okay, so let's see. E and ixx iyy minus I square xy whole square, that is common, right? From here, this into this after. Okay, so simply this we can take common. Why? Because with this term also this is there, right? And this term also is there. So once we will take, then for this one term and for this one we can take common, and that's why that becomes the whole square of that one. So whole square. Now what is left? The upper part, my1 my comma 1 ixx minus mx comma 1 ixy whole into x plus mx comma 1 iyy minus my comma 1 ixy into y, that is for sigma z1, into my comma 0 or not ixx minus mx comma 0 ixy into x plus mx comma 0 iyy minus my comma 0 ixx into y. Okay, that is here. Okay, so now let's see. After substituting those values, okay, so now just see here into what is there here, dA into dz. So after putting this, we have this one plus here. Okay, so this is for the first term. Then mx1, right, iyy minus my1 ixx into, so see here, after multiplying what happened? Two terms here, right, and two terms here. So every term will get multiplied with each term, or just let me, so for 1, this numerator part already we have taken common. Okay, 1 minute. So just write here. So see what we have to, what we will get, delta m, this I am not writing, 1 by e whole square. I am just writing this one, m y1 y comma 1 ixx minus mx comma 1 I x y. Okay, this is x. Okay, plus mx comma 1 I y y minus my comma 1 I y y into y. This term, this whole thing, this is just for this part, multiplied by what? This whole. So my comma 0 I x x minus mx comma 0, right? I x y, okay, into x, then with this plus sign m x comma 0 into I y y, okay, minus my comma 0 I x y into y. So now let's see, this into this whole thing into this whole thing, you have to multiply. So let's multiply with this first term, right? So this term with all the 4 it will get multiplied. Then this all the 4. Then this all the 4 here. Then this all the 4 here we have to multiply, and that only here it's get multiplied, right? This whole thing into first term, or just one by one. This whole thing, or let me clear this. Okay, so this whole thing into this one. Okay, this whole thing into this one first. Then this whole thing into this one. Then again this whole thing into this one. So if you will do like this, then only the 4 term will be there. Otherwise, you have to separately multiply with all the terms. Okay, so here just see, with two terms multiplied, this into this. Okay, and finally that whatever the integral part of that dz is there. Okay, for a section having either x or y axis as an axis of symmetry, right? If axis of symmetry for any is there, means what? That time ixy will be equals to 0 if axis of symmetry is there, right? If axis of symmetry is not there, then ixy will be there, not 0. Hence above equation reduced to, so wherever ixx is there, just remove to 0. So see here, after putting this ixy this term, so this whole term will get 0 because multiplication is there, right? The next ixy only, so this ixy is here, so this term also will be 0. Okay, now so here because it's a multiplication, now here this ix term will be, so this term will be 0. Okay, and then ixy, so this term also will be 0. So this term and ixy this term, ixy this term, ixy, okay, ixy, and this whole thing will be 0. So what is left? This term is left, this term is left, right? No, so after multiplying this also will be 0, right? So only 2 term will be there. So just see what is left here. And in this what we have taken as the constant, this also will be 0 after substituting xy. So finally we will get delta m equals to 1 by e integral of L my comma 1, right, my comma 0, okay, because that xx will get cancelled. So once we will multiply this to the 4th term by ixy plus mx comma 1 into mx comma 0 by ix into dz. Or if you have any doubt here, just simply put to first wherever ixy is there 0. So where we have to put 0? Here. Okay, so this term will be 0. ixy, this term will be 0, right? So what is left? If you will multiply this into this, that is here. Now this one x1 yy is there, but here xy is there and here xy is there. So once you will multiply that one, then what is left? mx1 and this one, right? That is there with iyy common. Now here this term will be what? xy, that is 0. Here xy, that is also 0. And overall this already it's multiplied by ix. So sorry, this ix is multiplied. So this term will be 0. Here my1 ixx into mx0 iyy will be there, right? That will be, so from here numerator, or just 1 minute, let me further explain, otherwise you will get confused. So see, I am just writing ixx0, right? Sorry, ixy0. So what is left here? my comma 1 into ixx, okay, and into this is need to multiply, so my comma 0 into ixx. So from here what we got? This one. right? This will be over. Now here Ixx is there, so this whole term will be 0 because all the multiplication, once we multiply with 0, that will be 0. This term also will be 0 because need to multiply with Ix. So what is left here? This term. So again, this term will be 0 and this term will be 0. So what is left? My comma 1, okay, into Ixx, okay, into my comma 1 into Ixx, okay, into mx comma 0 Iyy, right? So these two terms we have with the plus sign, okay. And what we have taken, that 1 by e into common, so just see this term, 1 by e into this whole square we have taken common, right? That is here, right? So what we have to do now, I'm just writing, so 1 by, putting here xy as 0, so 1 by e into Ixx into Iyy, okay, this whole thing. So this is in multiplication my comma 1 into Ixx into my comma 0 Ixx, right? So this term is with, or just I am taking this inside, just multiplying this individually, or just first term take normally, then we will see otherwise, plus my comma 1 Ixx into mx comma 0 Iyy. Now let's multiply this term inside. So now 1 by e, okay, so let's see I'm multiplying here, so this will get divided, so m 1 comma 0 into Ixx by, sorry, into my comma 0 Ixx, right? Whole divided by what we are getting here, Ixx into Iyy whole square, okay, plus this term because we are having a whole square, plus, so okay, let's simplify this term first, then we will simplify the second term. So what we have, this one, so Ixx cancel, Ixx whole square cancel, right? Now what we have, Iyy whole square, right? And this Iyy also will get cancelled similarly here, okay. Next for this one, mx1 comma mx0, so from here m, so this is for x1, right? And similarly for here you will get my comma 1 my0 as Iyy and Ixx, and then this z. So further simplifying, once you just expand or put the value without expanding and simplify, you will get this one. Okay, so finally this will be the moment equation, okay. So that means delta m will reduce to this one, okay. So the derivation of an expression for the shear deflection of thin walled section by the unit load method is achieved in a similar manner. So in the similar manner we can find for what, the unit by unit load method also. So there delta s will be equals to integral of L, okay, section, whatever the section you will take that section along that one, tau 1 gamma naught T ds. So see here, it's similar to that one, or what we have used here, this one, right? So it's similar. Again, just put the values and simplify, you will get that one. So by using this one, where tau 1 is the shear stress, that was for the direct stress. So this is for the shear stress at an arbitrary point S around the section produced by a unit load applied at the point in the direction of delta S, and gamma naught is the shear strain at the arbitrary. So tau 1 is the what, shear stress at an arbitrary point, gamma naught is the shear strain at the arbitrary point. So instead of this epsilon symbol, here they used gamma symbol. So don't get confused with gamma and all. Gamma is shear strain here at that arbitrary point where T1 we are considering, okay, corresponding to the actual loading system. The integral in parenthesis, so this part is taken over all the walls. So that's why it's a section is there, right? Whatever the overall cross section is there of wall of the beam. In fact, both the applied and unit shear load must act through the shear center of the cross section, otherwise twisting will be there. So otherwise additional torsional displacement occurs. So what we will apply, either it's a shear load or unit load that must be at the shear center. Otherwise what happen? Torsional will be there. So yes, we have to consider the torsional displacement also. So to avoid that complexity, what we did, we are applying the forces at the shear center. Okay, where shear load acts at other points, these must be replaced by shear load at the shear center plus a torque. So if suppose any load is acting somewhere, not at the shear center, so what we have to do, we have to ignore the twist in that torsion, right? So for removing torsion, what we will do, we will apply that force at the shear center, and from that point to the shear center, whatever the moment will be there, right, that we have to put there, right? So just that load will be converted to load into that torque. So just say load at the shear center plus a torque. That load into the distance will give the torque. So that we have to, so suppose shear center is here and applying the force, some force here F, right? So this force we can write here F, and suppose this length is L. So because of this force, whatever the torque will be there, that FL will also. So F plus FL will be here the total. Okay. Okay. The thickness T is the actual skin thickness and may vary around the cross section depending on how cross section you are using, but is assumed to be constant along the length of the beam. So along this surface, that along the skin, it's a varying, but along the beam, it's a just assumed because that is very small compared to the skin. So we are considering that as constant. Rewriting above equation in terms of shear flow Q1 and Q0. So now whatever the shear strain is there, just opposite to that one. So delta S 0 to L, again section Q0 Q1 by GT into ds into dz, just the previous equation, where again the suffix refers to the actual and unit loading. So Q0 is actual and one is the load unit loading system. In the cases of both open and closed section beam, the general expression for shear flow or long are best evaluated before substituting the above equation. So before substituting this equation, what happened? The general expression for shear flow and are long and are best evaluated means first evaluate there for the separately for shear. That's why, because for the closed one, hoop stress will be there. For open one, there is no hoop stress. So just first find that Q1, Q2 separately and then substitute here. Okay. So for an open section beam comprising boom and wall of direct stress carrying thickness TD. Okay. So Q0, this already we had seen. Q0 is what? So Sx naught. So just C naught is there. So in that naught, Sx naught, Sx comma 0, Ixx minus Sy 0, Ixy by Ixx, Iyy minus I square Sx into that same thing. Just here we have to replace. So 0 to S TDX into ds plus R equals to 1 to N BR XR minus Sy naught y comma 0 Iyy minus xx comma 0 Ixy by Ixx into Iyy minus I square xy whole into integral of 0 to S T d y ds. You see everything is same, just you have to remember x and y is different. So first term x minus second term y. So wherever x s is there, just replace with y. So now here Td and x, that x becomes y here, ds plus R equals to 1 to N, that again sigma R equals to 1 to N br yr. Right, this already we had seen. So now this is for Q0. Similarly for Q1, what? Minus Sx comma 1. So now not that 0 replacing or not replacing to 1. So Sx comma 1 Ixx minus Sy comma 1 Ixy by Ixx into Iyy minus I square xy. Okay, whole multiplied by 0 to S, that integral of Td into x. Td is thickness, not T into D. Td is subscript. Okay, Td into x into ds plus sigma R equals to 1 to N br xr. Okay, minus Sy comma 1 Iyy minus x comma 1 Ixy by Ixx Iyy minus I square xy. Okay, whole multiplied by 0 to S Tdy ds plus sigma R equals to 1 to N br yr. So this will be the final Q0 and Q1. Now, so just see what substitute here. So this whole thing, okay, multiplied by this whole thing. Okay, that will give you Q1 Q0 into ds by gt into dz. Then you will get the final that delta S value. Okay, so similar expression are obtained for a closed section beam also. Closed section beam, what we have to do? We have to just QS comma not that hoop stress value. So with that we will get for the closed section beam also. Okay, so here, so let me once recall. Okay, so the delta T is just T naught T1 by Gj into dz, where J is the torsion constant, and by this method we can find for unsymmetrical as well as symmetrical using the complementary energy equation, and there what we are using the unit load method. Okay, so that you have to remember here we are using the unit load method. So from that one, virtual unit load, this already we had seen in the what complementary energy equation. So from here this, and this one stands for the unit load method, that moment equation. Alright, so this overall should be for the equilibrium. What happens, this equation and this overall should be equals to 0, right? So just equate it to 0. So after equating to 0, just take this to this side, so this will be equals to this one that we got here. Okay, so now after that, just putting the value of sigma z and epsilon z or gamma z, you can say. So sigma z1 we required. So sigma z1 already we found in the previous equation. There you have to just in terms of my, that time also I told you, if depending upon the requirement, you can use in terms of what, sigma or load Sx, right? So here we are using moment and load. So here we are using in terms of a moment. So my comma 1 Ixx and this one. Similarly for epsilon, that is what, strain. So strain is what, stress by strain. So already we found a stress. So that is for first that unit point. Here that is for 0. So everywhere just wherever 0 is there, 0 replace and divide whole thing by epsilon naught. You will get a strain at comma 0. So 0 and the actual load. So what is 1 and 0? 1 is for unit load and 0 is for the actual load. Okay. So after that, just simplify this one. Just substitute these two in this equation. Okay, so what happens, this whole thing will get multiplied by this whole thing into dA into dz, that for delta multiplying. So after taking this whole square, because why? Because with this term also this is there, this term also is the same. So once we will multiply both, then their whole square will be there. So after taking whole square common, now just multiplying and substituting Ixy because of the symmetry, right? X and y axis will be there, not xy. So Ixy put 0. So after putting Ixy 0 here, after simplifying, you will get delta m value, this one. Okay, so in a similar way, we can find for the what, closed section also, right? So the delta is equals to 0 to L section. Now tau 1 gamma naught TDS. So here tau 1 is what, shear stress, and gamma naught is what, the shear strain, right? Gamma naught is the shear strain. So in the same way, first find the tau 1 naught and gamma naught and substitute here. Okay, and in case of for the what, open section, so just see in terms of shear flow distribution. So delta S will be equals to what, Q naught Q1 by G2 into ds into dz. So again, what is required, Q1 and Q2. Just find Q1 and Q2 from the same equation, that shear flow distribution, and substitute here. So what is Q1? So Q naught. So everything just where you have to replace with the naught. So Q1 in terms of stress this time, sorry, load. In terms of load we are using here. So load Sx for Q0 we are finding. So here Sx naught. For Q1 we are finding. So Sx1. Similarly, so wherever, and this whole thing remains common for the same. Same expression can be found for what, closed section also. Why? In that closed section only just we have to introduce the stress. That's all. Remaining everything will be same. Okay. So that I will show you in next video also how to find for the closed beam. Okay. So is there any doubt? You can just comment on the video, or you can just contact me so that I can clarify your doubt. Okay. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.